The echo of awareness is the universe observed into being by the consciousness that wove it. The question, perhaps the most profound and persistently seductive in the history of human inquiry, cuts across the chasm separating physics from philosophy, materialism from idealism, the objective cosmos from the subjective self. Is the universe we perceive, measure, and mathematically model, fundamentally contingent upon the act of observation itself? Implying that consciousness is not a mere epiphenomenon of complex neural structures, but rather the foundational substrate from which reality precipitates. This query demands a journey through the most unsettling frontiers of quantum mechanics, through the labyrinthine corridors of cosmology, and into the nascent, sometimes controversial, territories of integrated information theory and panpsychism, all while maintaining a rigorous adherence to the empirical evidence currently available, however paradoxical that evidence may seem. We must begin where the classical worldview, Newtonian and deterministic, definitively fractured, the quantum realm. The standard model of particle physics, an edifice of extraordinary predictive power, rests upon mathematical formalisms that describe reality not in terms of definite states but in terms of probabilities. Wave functions, mathematically represented by the Greek letter psi, the state vector, evolving deterministically according to the Schrödinger equation. This evolution, however, describes the potentiality of a system, not its actuality. The transition from potentiality, the superposition of multiple, mutually exclusive states, to a single, definite outcome, is the notorious measurement problem, the Gordian knot of quantum theory. Consider the double-slit experiment, the quintessential demonstration of wave-particle duality. When electrons, or even larger entities like buckyballs, are fired at a barrier with two slits, they produce an interference pattern on the detector screen, characteristic of a wave passing through both slits simultaneously, a state of superposition. Yet, if a detector, however minimally intrusive, is placed at the slits to ascertain which path the particle takes, the interference pattern immediately collapses, and the particles behave like classical bullets, yielding two distinct bands. The act of measurement, the very engagement of an observing system, seems to force a choice upon reality. The Copenhagen interpretation, historically dominant, posits that the wave function collapse is a fundamental, irreducible postulate of quantum mechanics, an abrupt, non-unitary transition occurring when a quantum system interacts with a macroscopic measuring apparatus. John von Neumann formalized this view, suggesting that consciousness itself might be the ultimate, non-physical agent required to complete the measurement chain, though subsequent interpretations have sought to localize the collapse mechanism elsewhere, notably within decoherence. Decoherence, a process explained by the environment rapidly entangling with the quantum system, effectively isolates the system's quantum coherence into a vast, complex entanglement with the surroundings, making the interference effects practically undetectable by any macroscopic observer. The system appears classical because its superposition is spread too thinly across countless degrees of freedom in the environment. However, decoherence explains the loss of coherence but not the fundamental act of choosing a definite eigenvalue from the spectrum of possibilities described by the Hamiltonian operator. It shifts the problem from the observer's mind to the environment's complexity, yet the fundamental probabilistic nature remains unresolved until a definite result is recorded. If consciousness is the ultimate observer, as some early interpretations suggested, we venture into the realm of idealism, a viewpoint perhaps best articulated by physicists like Eugene Wigner, whose famous thought experiment involving a friend in a distant laboratory underscores the ambiguity. If Wigner measures a particle's spin in his lab, the wave function collapses for him. But for his friend who has not yet received the measurement result, the friend's lab, including Wigner and the particle, remains in a superposition of states until the friend opens the envelope containing Wigner's data. Where, precisely, does reality become definite? Wigner suggested that only the subjective awareness of the final observer solidifies the outcome. While this view is often critiqued for introducing an unscientific, metaphysically privileged role for the mind, it highlights the uncomfortable boundary condition inherent in the quantum formalism. Conversely, the many worlds interpretation, formulated by Hugh Everett III, seeks to eliminate the collapse postulate entirely. In this interpretation, every time a quantum measurement occurs, the entire universe splits into branches, one for every possible outcome of the measurement. If a photon hits a beam splitter, one universe continues where the photon went left, and another where it went right. There is no collapse, all possibilities are realized, each in its own non-communicating branch of the universal wave function, which evolves strictly unitarily according to the Schrödinger equation. While mathematically elegant, the ontological extravagance of positing an infinite, constantly branching multiverse strains credulity for many, offering an answer that dissolves the problem by multiplying realities exponentially. The challenge remains, why do we, the subjective observers embedded within one branch, perceive only one definite history? Moving beyond the immediate implications of quantum measurement, we confront the architecture of spacetime itself, the arena where these quantum events unfold. Modern cosmology, anchored in Einstein's general relativity, paints a picture of a dynamic, evolving universe governed by the field equations relating the geometry of spacetime, represented by the Einstein tensor, to the distribution of energy and momentum, represented by the stress-energy tensor. The standard model of cosmology, lambda CDM, which incorporates a cosmological constant lambda representing dark energy and cold dark matter, describes a universe originating from a singularity, the Big Bang, approximately 13.8 billion years ago, which has been expanding ever since, currently accelerating its expansion due to the mysterious repulsive force of dark energy, estimated to constitute around 68% of the total energy density of the cosmos. However, the very beginning, the initial singularity, represents a boundary where general relativity breaks down due to infinite spacetime curvature and density. To describe this epoch, a theory of quantum gravity is necessary, a theory that successfully marries the smooth, continuous geometry of the macroscopic world with the quantized, probabilistic nature of the microscopic world. String theory and loop quantum gravity are the leading contenders, yet neither has achieved empirical verification to definitively replace general relativity at the Planck scale, which is roughly 10 to the negative 35 meters and 10 to the negative 43 seconds, scales where quantum gravitational effects become dominant. If quantum gravity theories suggest that spacetime itself is quantized, existing as discrete loops or vibrating strings, then the concept of a pre-existing, continuous background against which consciousness acts becomes dubious. If space and time emerge from something more fundamental, then the question shifts, what is this substrate, and is consciousness intrinsic to it? This brings us to the concept of the fine-tuning of physical constants. The fundamental constants of nature, the fine structure constant, the ratio of the electron mass to the proton mass, the strength of the gravitational constant, the cosmological constant, must fall within incredibly narrow ranges for the universe to permit the formation of complex structures, stars, chemistry, and life capable of supporting observers. For example, if the strong nuclear force were just a few % weaker, carbon, essential for life as we know it, could not form inside stars via the triple alpha process. If the cosmological constant was significantly larger, positive or negative, the universe would either immediately recollapse or expand too rapidly for galaxies to coalesce. This astonishing alignment leads to the anthropic principle, often invoked in two forms: the weak anthropic principle, which states that the universe must have properties compatible with the existence of observers, a tautology, and the strong anthropic principle, which suggests that the universe must have properties that allow life to arise at some stage. Many physicists interpret this fine-tuning through the lens of the multiverse hypothesis, suggesting that our observable universe is but one bubble in an ensemble of universes, perhaps generated by eternal inflation, each possessing different physical constants. In this vast landscape, it is inevitable that some universes will support life, and we, by definition, must inhabit one of those life-supporting bubbles. This explanation elegantly sidesteps the need for a conscious architect, replacing it with statistical inevitability across an unobservable ensemble. However, The multiverse, while statistically compelling in some inflationary models, remains fundamentally untestable under current paradigms because, by definition, the other universes are causally disconnected from ours. If empirical science demands falsifiability, the multiverse risks sliding into metaphysics. This opens the door again to alternative, potentially more direct explanations involving consciousness. Consider the panpsychist perspective, or variations thereof, which suggest that consciousness, or proto-consciousness, is a fundamental property of reality, perhaps existing at the level of elementary particles or fields, rather than emerging solely from complex biological organization. If this were true, then the universe is not merely being observed by consciousness, it is, in a sense, pervaded with awareness, which constitutes its very substance. The complex, self-aware consciousness we experience in human beings would be an integrated, highly organized form of this universal proto-consciousness. This idea gains traction when considering the binding problem in neuroscience. How do billions of disparate neural firings in the brain coalesce into a single, unified, subjective experience? Integrated Information Theory, or IIT, developed by Giulio Tononi, attempts to quantify consciousness using a mathematical measure denoted by the Greek letter phi, the integrated information content of a system. IIT posits that any system that possesses a high degree of integrated information, meaning it has a large repertoire of internal states that are richly interconnected, irreducible to independent components, possesses consciousness. If IIT is taken seriously, consciousness is not exclusive to biological brains, it is a spectrum, potentially inherent in any sufficiently complex, integrated structure. If this concept extends down to fundamental physical entities, then the universe itself, perhaps in its unified quantum state, possesses some form of primitive phi. If the universe possesses intrinsic information structure, how does that relate to observation? If the universe is information, as suggested by Wheeler's it from bit, where physical reality arises from yes or no answers to quantum yes or no questions, then the observer plays a crucial role in eliciting those bits. The observer does not merely passively record a pre-existing state, the act of observation helps define the information content of the system. Let us delve deeper into the implication of the observer effect in information theory applied to cosmology. If the universe is fundamentally informational, then the measurement problem is the process of information becoming definite and localized. Cosmological data itself is fundamentally informational. The cosmic microwave background radiation, the faint afterglow of the Big Bang, provides us with a snapshot of the universe when it was only about 380,000 years old, at the surface of last scattering. This radiation field, which exhibits minute temperature anisotropies, the density fluctuations that seeded all later structure formation, is itself subject to quantum mechanical uncertainty before being measured or realized. The statistics of these fluctuations are exquisitely predicted by inflationary theory and match observational data from missions like the Planck satellite to an astonishing degree. The question is, did those specific fluctuations exist in a definite state before the first photons decoupled from the plasma and began their journey toward our detectors? Or is the specific configuration we observe the result of a cosmic scale measurement process? Some speculative cosmological models suggest that the universe exists in a superposition of possible vacuum states or inflationary histories, and the emergence of our specific reality, with its specific set of fine-tuned constants, represents a selection mechanism inherent in the act of coming into being, or being measured by the structures within it. This line of reasoning invokes the concept of self-reference. If the universe is to be completely described by physics, and physics includes quantum mechanics, then the description must eventually include the observer doing the describing. If the observer is part of the universe, the description becomes recursively defined. The physicist Sean Carroll, while a proponent of the many worlds view, acknowledges the profound difficulty in consistently applying quantum mechanics to the entire universe without invoking external concepts. If the universe is a closed system, then its state vector should evolve unitarily forever, implying no collapse. Yet, our experience testifies to a collapsed reality. This suggests that either our concept of a closed system is flawed at the cosmic scale, or our understanding of collapse is incomplete. Consider the implications of quantum gravity on the nature of time. In canonical quantum gravity approaches, time often emerges as an internal degree of freedom, rather than an external parameter ticking uniformly, famously encapsulated in the Wheeler-DeWitt equation, which, in its simplest form, appears timeless. If time itself is an emergent property tied to change and measurement, then the universe does not unfold in time. Rather, the experience of unfolding, the sequence of observations that builds history, is what we call time. The universe, viewed from outside its own temporal framework, might exist as a timeless block of potential states, actualized moment by moment through observation. If we lean into the informational perspective, that reality is fundamentally combinatorial, built from discrete yes-no answers, then consciousness acts as the ultimate interrogator. The universe presents a vast, high-dimensional wave function of all possibilities. When a conscious system interacts with a small subset of this information, extracting a specific datum, that datum becomes real for that observer, and potentially for the localized section of the universe connected to that observer through entanglement. This interpretation is not wholly dissimilar to certain interpretations of quantum mechanics applied to black holes, specifically the information paradox. Stephen Hawking showed that black holes radiate thermal energy, Hawking radiation, suggesting that information about the matter that fell in is permanently lost when the black hole evaporates, violating the unitary evolution of quantum mechanics. While the firewall paradox suggested a violent resolution at the event horizon, modern string-theoretic approaches, particularly those involving ADS-CFT correspondence, strongly suggest that information is preserved, encoded holographically on the event horizon. The holographic principle, a concept derived from black hole thermodynamics, posits that the description of a volume of space can be encoded on its boundary surface. If the universe itself can be described holographically, then our three-dimensional, time-evolving reality might be a projection of a simpler, perhaps more fundamental informational structure residing on a distant boundary surface, a boundary that might itself be informational and potentially linked to the constraints imposed by observation. Let us return to the experimental evidence, or the lack thereof, which forces us to remain speculative. Experiments designed to test the limits of quantum mechanics, seeking to observe the transition point between the quantum and classical worlds, Schrödinger's cat in a macroscopic superposition, for instance, consistently push the boundary further into the quantum domain, never quite finding the hypothesized boundary where observation must intervene. Continuous observation experiments utilizing quantum optics have shown that the collapse is extraordinarily fast, but the role of the conscious aspect of the observer remains scientifically untestable because any physical interaction required to register a result involves an uncontrolled environmental interaction leading to decoherence. However, the philosophical drive remains potent. If the physical description of the universe relies fundamentally on probability until a measurement is made, and if the universe contains all the necessary components for that measurement, including conscious beings, then the description of the universe must inherently include the self-referential act of observation. The search for a theory of everything often assumes an objective reality existing independently of us. But what if that assumption is the very obstacle? What if reality is not a noun but a verb, an ongoing, participatory process? Consider the implications for emergence. In a purely materialist view, consciousness emerges from non-conscious matter when complexity reaches a critical threshold, e.g., the 3-pound electricity conducting mass of the human brain. In this view, observation is simply a physical computation performed by a complex system that has evolved to model its surroundings. The universe existed long before this computation began, and the quantum probabilities were resolved by the interaction of physical systems, the measuring device, with the measured system, regardless of a mind registering the result. But what if the information transfer required for decoherence is fundamentally linked to the creation of subjective experience? If IT is correct, and consciousness is integrated information, then the universe, prior to complexity, possessed only primitive, minimal phi. The moment the universe became complex enough to form self-referential loops, whether through gravitational collapse into stars or chemical complexity leading to life, it began to observe itself in a meaningful way. And this process of self-observation might be precisely what drives the definite realization of physical states. The universe, in this sense, is a feedback loop. It generates structures capable of measuring it, and those measurements solidify the reality that allowed those structures to form in the first place. This perspective forces a reconsideration of the cosmological constant, lambda, the term representing dark energy, which is bafflingly small yet non-zero. Theoretical predictions for the vacuum energy based on quantum field theory yield a value wildly different, some 15 orders of magnitude too large, compared to the observed cosmological constant. This discrepancy, often termed the worst theoretical prediction in the history of physics, is often resolved by invoking the anthropic principle and the multiverse. But if observation plays a fundamental role, perhaps the vacuum energy, the baseline energy density of empty spacetime, is itself dynamically related to the total integrated information or the level of observational activity within the system. If the universe is perpetually observing itself, defining its own boundaries and metrics through this process, then the observed value of lambda might be an equilibrium state reached through this continuous process of self-actualization. The predictive power of current physics, while immense, remains fundamentally incomplete because it excludes the conscious subject from its completed mathematical description of the objective world. Quantum field theory, general relativity, and the Standard Model are magnificent descriptions of what happens under specific conditions, but they skirt the ontological question of why these mathematical potentials resolve into the single actuality we inhabit. If we entertain the possibility that the universe is observed into being by the consciousness that weaves it, we are proposing a form of participatory realism, moving beyond passive realism. The world exists regardless of observation, and subjective idealism, only my mind exists. Participatory realism suggests reality is co-created through interaction. The information constituting the world is relational, existing between the observed system and the observer. Consider the implications for time's arrow. Physics equations are overwhelmingly time-symmetric, meaning they work just as well running backward as forward, except for the second law of thermodynamics, which dictates that entropy, or disorder, always increases in a closed system. This irreversible increase in entropy defines the psychological arrow of time. We remember the past, not the future. Could the increase in entropy simply be the physical manifestation of the increasing informational processing, the relentless observation or instantiation of definite states across the cosmos? Each measurement extracts information, increases complexity in the observer's local environment, a slight increase in entropy, and drives the system further along the one-way street of definite history. The universe runs forward because it is constantly forcing itself out of superposition into concrete actuality, one quantum event at a time. The pursuit of this idea leads us into the more esoteric realms where physics brushes against metaphysics, specifically regarding theories of consciousness that posit non-locality. If consciousness is truly fundamental, perhaps it is not strictly confined to the biological substrate but is entangled across the universe, a shared informational substrate. This sounds suspiciously like mysticism, yet, if quantum entanglement, where two particles remain linked regardless of spatial separation, is a universal feature of reality, perhaps integrated awareness is also fundamentally non-local. If we synthesize these threads, the necessity of collapse in quantum mechanics, the fine-tuning problem demanding explanation, the informational nature of quantum states, and the subjective unity of experience, the conclusion, however uncomfortable for staunch materialists, becomes logically compelling as a possibility. The universe requires an internal process of self-measurement to transition from potentiality to actuality. The most direct implication of this view is that the universe is not merely governed by laws, it is actively participating in its own realization through the emergence of measuring apparatuses, which are themselves conscious entities. The universe observed itself into existence through the evolution of complexity capable of asking the question, "What am I?" To construct a predictive framework based on this hypothesis, that observation defines reality, would require a revolutionary shift in physical theory, perhaps one where the Hamiltonian operator itself becomes dependent on the entanglement structure of the entire system, including the informational degrees of freedom associated with awareness. Such a theory might explain why the cosmological constant is so small. Perhaps the ongoing, low-level self-observation of the universe maintains a delicate balance against the overwhelming drive toward vacuum energy predicted by quantum field theory. The universe, by being observed, stabilizes itself into a structure capable of sustaining further observation. In conclusion, while the empirical sciences currently operate successfully under the assumption of an external, objective reality that consciousness merely reflects, the deep structure revealed by quantum mechanics suggests that this assumption is an approximation, valid only at the macroscopic, decohered limit. The ongoing debate surrounding the measurement problem, the puzzle of fine-tuning, and the intractable nature of quantum gravity all point toward a missing piece of the puzzle. A piece that may not be a new particle or a new force, but a fundamental revision of the relationship between the knower and the known. The universe, in its dance of creation and collapse, may indeed be the ultimate self-observing entity, where every photon, every galaxy, every fleeting thought, is both the product and the necessary instrument of its own magnificent manifestation. The echo of awareness, if it exists at the foundation, suggests that existence is synonymous with perception, and the cosmos is, therefore, a continuous act of self-contemplation.